So one thing I really want to work towards is wind tunnel and AR. And so in order to do that, we need fluids, and we also need to be able to get depth information into our fluid simulation. So that's going to be a lot of what today's about. The one thing though is that usually you do incompressible fluids as a learning step before compressible fluids. So things like liquids before you actually end up doing things like gases. And so this is going to focus a lot more on the liquids. This would only really apply if you had your car underwater or something. So there's gonna be some extra video later where I do some more, but that's what we're gonna get up to today. We have a little bit of groundwork that we need to lay before we actually get to the topic. And so just some previous things that we had worked on that we will be using throughout this. So we previously made a grid with the depth information, and that is going to be used as our method for interaction. So we will need that. We also do need to do the stuff with the server that we did there. So we are going to be solving these equations in Python, and then we're going to be sending them back to JavaScript. So for the fluid equations, we're going to be using the super famous paper from Jose Stam, who did stuff with stable fluids back in 1999, and it still holds up today. And so in particular, we're going to be using a video that someone had put out fairly recently on this topic, and we'll be using that as kind of a starting off point. So they did it in 2 dimensions. We need to do it in 3 dimensions. There's going to be some modifications that we need to make, and then there's also just kind of some things where they're doing it in a kind of continuous loop, and they're initializing their forces in a different way than we will be. So we have to make some modifications of it, but the kind of core idea, like I want to make sure that I'm not saying that I did this all on my own. There was a lot of previous work that had gone into this. So I'm standing on shoulders of giants type thing here. There's a really nice blog post by Jamie Wong that goes over the different aspects of fluids and how they all interact. So just playing around a little bit with those will give you a much better idea of what is happening. It also helps to highlight the fact that we are calculating out velocity fields and we aren't actually calculating out the material flow. And so that's something that a lot of times when people look at liquids, they are looking at material flow and not the vector field. So if any of our results look a little bit weird, that's probably the differences that are being made. I started doing fluids with just a Python script and then plotting it with each frame, so using matplotlib, and then I made some animations for that to see how it was working out. So the first time around I ended up running into this difficulty where there was a larger spread on the angles on the diagonal than I would have expected, and so that came down to an indexing error. So I just had to flip that around, and then everything ended up working out much better. Once we finished with the Python, we moved on to augmented reality, and the first thing that I recognized is that the motion of the plume of the velocities was traveling tangentially to the velocity, which is kind of unexpected, and so I had to look into it again, and then it was another indexing error. So be very careful with your indexing when you're doing things like this. It's common mistakes, and they're also a little bit annoying because they don't throw any sort of errors, so you don't get any sort of lead in the actual... That's a common mistake that can happen. So just be a little bit careful with that. Once we fixed that issue, everything was pretty smooth sailing. One thing that I'm not sure I actually appreciated enough is I tried to implement a smoothing function and it isn't as smooth as I would like. So you can notice that the AR is actually pretty smooth, but there's some hiccups because the networking causes some frame drops. It's very low frame rate from the server to the user. So that's something that I need to work a little bit on. It is mostly a networking problem. So it's not actually a computation problem. We're not running into computation limits. We're running into networking limits. So that's why it's a little bit stuttery, and also the smoothing function was not as clean as I would have liked, so it had a little bit of hiccuping and that didn't make it look as nice as I would like. Another thing I wanted to remind you of is these are the vector fields and they are not the flow fields. So if there are things that look like they are moving a little bit slow, generally the velocity field ends up moving slower than the flow of the actual liquid. Like if you watch a vortex, it ends up moving rather slowly. And finally, I wanted to show that the boundary conditions are updating continuously, and this example didn't look as nice as I was hoping, but you can actually see that the chair kind of blocks the fluid, so it is something that is live updating. The thing that's a little bit of an annoyance is that the way we're implementing the boundary conditions is that we're using a shell, so it's the shell of the chair, and so things that are, if you move it past the liquid, the liquid will continue on the other side of it, so I should have made it more of a solid than a shell, but that's just something to keep in mind on why it might look a little bit strange. So that's something to consider too, is whether we should be using shells or solids. And it is a little bit of a confusing question, because if you use solids, then you end up having boundary conditions behind the object, which might not be what you want. So that's something to just think about. But perhaps even doing 2 or 3 layers would be beneficial to avoid leakage, because right now you can actually have objects leak through the boundary conditions because the boundary conditions are generally just 1 pixel thick, 1 voxel thick. So we're going to start with the Python code. So there's quite a few imports. The imports that are kind of new are going to be the interpolation, the scipy solver, and scipy and numpy. And then for the initializations, we have a few different values related to the size of our scene, some things that kind of give the positioning and the sizing. And then for the math, we need to initialize a discrete Laplacian, initialize the initial boundary conditions, and some things with the potentials. And then we have to do some things to get our coordinates in the right area, and then we will have a value for velocities and a value for scalars. So the velocities are just going to be the velocity of our liquid, so that's oftentimes referred to as u in literature. And then we have scalar, and that's mostly going to be used to hold the pressure. And then we have some indexing and some mesh grids. So the mesh grids, the indexing actually was associated with quite a few different errors that I had throughout. So that's just a line that you should probably keep in mind. Next up is a lot of the code that's associated with the potential or the boundary conditions that we had made. So this is a lot to do with converting the depth information into boundary conditions that we can use. Next up, we initialize some variables that we're going to be using for the liquid. So in particular, our dt and our viscosity, and the dt is going to be changed throughout. So we're going to define fluid function, which will update our fluid, and that has 2 different global variables, the force field and the velocity. So the first step we're going to make is decrease the force field. So we want our force field to be something that that decreases over time. So unless we're constantly adding force, it'll dissipate over time. And so we're just going to multiply it by a value, and that'll lower it. The next step is adding our force. And so that will just be a simple Euler step where we take our current velocity and then we add the force field times a small increment in time. And after that, we have to apply the boundary conditions. So our boundary conditions is going to be an array of true and falses. And wherever it is true, we will just set the velocity to 0. So this is the same as a non-slipping condition. The next up is we are going to do our advection function. And so our advection function uses itself to advect. So we use our velocity field, we project it backwards in time, and then that gives us a backtrack position, and then we interpolate those values forwards in time. So once we have that done, we are going to apply our boundary conditions again, because it could have ejected into our boundary condition, and then we will do our diffusion. So our diffusion is going to be a conjugate gradient. So this is an AX equals B type problem with A and B being matrices. So the fourth step is to project it into a space where the gradient equals 0. So this is the step where we are using the fact that it is a incompressible fluid. And so to do that, we need to get the pressure, and the pressure is going to be very similar to the last step where it is also a conjugate gradient, but this time we are using a Poisson function to do that. And then we are subtracting that off of the diffusion, the velocities that are diffused, and that should give us the projected thing. So now I just wanted to go back and look a little bit over more detail on what the add, diffusion, and Poisson functions look like. So the diffusion step requires us to calculate out the Laplacian. So we're going to use our discrete Laplacian. The ut sign there is a matrix multiplication. So we matrix multiply it, then we subtract it with a small amount of time difference and the viscosity, and we subtract that off of the vector field. And so now that is the diffusion applied. And then once again, we apply the boundary condition. For the pressure, we are using the divergence and the Poisson. So the Poisson is, once again, the discrete Laplacian times the flattened field. And then the divergence is just going to be using a partial differential equation on the field for each different index. So we are going to be doing it for x, y, and z. So our numerical partial differentiator is what we're calling partial. And so this is going to be using a 2-point formula. So we are taking 1 step back, 1 step forwards, and then we're dividing it by 2 unit lengths. points, and we are using the outside is going to be set to 0. So that's setting the boundary conditions of the side of the boxes to 0. And that gives us our partial differentiator. So I didn't set the boundary conditions to equal 0 after the pressure step, because at this point the gradient should be 0. And so if we start setting things 0 after we make the gradient 0, then we might end up with a non-zero gradient. And I think that would cause some issues. So I'm a little bit unsure about whether to apply the boundary conditions after the pressure step or not. So that's just something to keep in mind, that maybe I am doing that part. Yeah, that's something I'm a little bit unsure about. Now that we finished all the math, we can start working on our requests. So to start off with, we need to do some time changes so that we get each time steps. We just need to find out what the amount of time that has elapsed between this step and the last step is. And then we have to update our global conditions and our force function, or our force field. So to start off with, we're getting the image. So this is going to be the depth image. We're going to get the pose. So this is going to be the value of the actual camera. And then we are going to get an action variable. And so this is what extra buttons are being pressed, and it's related to our UI. So if the force button is being pressed, we are going to add we're going to change our force field to be a static value. And then if the reset button is clicked, we are going to set our velocities to 0 and our force field to 0. Then we are going to get all of our values from our pose, and we're going to put it into our potential function, and that'll give us our V value, which is a value that has either 0 or a larger value if there is something present in the grid. So it is going to basically turn our depth information into a floating cloud of points, and those points are attached to a grid. If points are above 0, we are going to turn it into a true condition or a false condition. So that is what this next step is for the boundary conditions. And then we are going to do our fluid update, and that'll give us a velocity, and we are going to turn that to a set of lists, turn that into JSON, and then send it back. So we are sending back the velocity. This JavaScript is very similar to some of the things we've done in previous projects. So we're going to initialize a grid of lines, and then we'll also have a set of new positions, which is going to be associated with the positions, so that we can kind of lerp all of our values together. So we can kind of interpolate our old values into our new values and make it look a little bit smoother. So for the XR frame, the things that we're going to be adding to it is we have to have our depth information, and then we are going to be gathering whether the reset button has been pressed and the force button has been pressed, and then a bunch of information about the camera and where it is positioned and the depth information. And we're kind of combining all that information together, and then we're updating the server. The information we get back from the server, if it is paused, we will not actually update the plot, but otherwise what we'll do is we apply our updating function, and that basically just sets the new positions to what the old positions were, and then it sets the new positions to be a value that's added to the origin of each point. So basically we are plotting the vectors on top of the start of the line segments, and so that will move each line segment according to the velocity that we've given it. One of the issues that comes up with this method is that we have a different clock rate for our server versus what's actually happening in our scene. And so I tried to do some FPS matching, so some frames per second matching, where we would match the scene FPS to our server FPS and then lerp between the two. So we would have linear interpolations to get from our values to from our server values to our actual scene values. So our server, the FPS is like between 2 and 3, versus our scene should be closer to 20 to 60. So that they're somewhere in between there. And so we need to increase it a bunch. And so I tried using this lerping method. It didn't work as well as I was hoping. So I also wanted to add that the main source of FPS slowing is actually a network issue. So if you don't network this, you can actually get up to about 8 or 9 FPS for the server without the networking. So if you assumed networking was perfect, then it would be 3 or 4 times as fast. So this is our lerping step. So we are changing the lerping value as we go, and we are just lerping between the old position and the new position, and that should give us a lerp value that looks a little bit smoother. And so, yeah. And then at the bottom, we're just adding in a bunch of these different event listeners. So we have some clicks and some very basic, just kind of holding functions and stuff like that. Thank you, and have a great day.